Good afternoon. My name's Ed. This is Dan. We're going to be talking today a little bit about the current state of virtualizing network monitoring. This talk isn't as cool and sexy as brand new vulnerabilities, but this is a little bit more on the engineering side of where the future, we think, of network monitoring is moving to. We got the after lunch snooze slot here, so we'll try to keep it a little bit lively as much as a couple of engineers can. Okay, so the first thing is why are we even talking about this? Why are we even talking about virtualizing network monitoring? So the reality is that virtualization is here, right? It's not going anywhere. It's only becoming more prevalent. And there's two major reasons that we're looking at specifically network monitoring in a virtualized environment. The one is that the data is moving to virtual areas, so we have to move the network monitoring to where the data is. The second reason is that the same benefits that that applications get from virtualization, we can actually, in the security community, we can benefit from that as well. That's things like scalability. That's things like fast deployment. Right now, you can go to something like Amazon or Rackspace and spin up an application in a matter of minutes. And a lot of times, us in the network monitoring security community, if we want to deploy a new IDS or whatever, sometimes it takes months, right? So we're trying to get better at this and improve upon the way that we do deploy new tools and new techniques in the same kind of fashion of leveraging the skills that the capabilities that virtualization has brought to applications. So again, why is this important? So it also allows us to do right sizing. So in the world of network security, we're talking firewalls, IDSs, web content filters, full packet captures, net flow monitoring, all those kind of capabilities. A lot of times right now, those are actual hardware appliances, right? So the problem with the hardware appliance is bandwidth is moving really fast right now, right? So a lot of times, as a entity grows, it needs to pick up more bandwidth. So you might start out like a small company might have a 100 meg pipe, but if that company grows, suddenly it's got a 1 gig pipe. It continues to grow, suddenly it's got a 2 gig or 3 gig pipe. And every time you have that kind of growth, the ability to scale, like a new Cisco firewall or a new Palo Alto or Surcot or whatever, a lot of times you have to rip and replace, right? Okay, we're upgrading to 2 gigs. Well, my firewall only has a 1 gig port, so I've got to rip and replace. And again, we're talking about multi-months of deployment. So virtualization allows us to kind of right-size that, right, and scale out a little bit better. That's the same reason that applications move towards the cloud. There's this new, these new NFV and SDN, and I'm going to try not to use the term SDN too much because it is way overused. Everybody's saying they do SDN right now. It's never really been defined, but it is something that is applicable to us as network monitoring folks. The last thing is that we wanted to see if open source was really ready to meet all the requirements. So we took a look at a lot of things that Dan's going to talk about. We kind of hobbled together a ton of different open source tools into one big virtualized monitoring, and just to see what it can do. So with that, I'm going to turn it over to Dan real quick, and he's going to cover some of the awesome stuff that he's been working on.
So we individually built 2 prototypes. The first one was we're going to build an all-in-one type solution. So we wanted something that did the IDS monitoring, all the packet flow that you would expect from an enterprise, correlate all the logs together, put them in a single central repository, have a way to query out the information, search, and so forth. So that was our first solution that we're going to talk about. The second solution is we wanted to build as big of an IDS / bro box that we possibly could. So in this situation, we were more concerned with how much bandwidth can we actually process out of a single virtualized instance. And that's going to be the second project we're going to talk about. Both of these projects were between $3,000 to $4,000, which, depending on who you are, that may or may not be cheap. But we wanted to just show what was possible. All the software that we used was freely available online, so there's nothing in terms of licensing costs. So we all our money was in hardware costs alone. The first solution, this is what it looks like. It's very portable. I'd say it's a little bit bigger than a six-pack of beer. I even put a picture of a beer in there just so you get an idea how large it is. It's not very large. It probably weighs about 20 pounds or so, and can be used as a portable type solution. The specs for it is an 8-core Xeon D. If anyone's familiar, Xeon Ds are relatively new. They're very low powered, Intel chips. The one we went with is about 45 watts. It has two 10 gig interfaces and two 1 gig interfaces. This particular system, we put 128 gigs of RAM in it because it's going to be kind of doing everything. And 24 terabytes of raw storage in RAID 10, so that halves it. And then we also, to keep up with the performance, we put in an 800 gig enterprise SSD cache drive. So it doesn't actually add anything to the storage. What it does is it speeds up the disk performance so that it can actually keep up. And if you pull the cache drive out, the whole thing comes crashing down because it can't keep up. So the cache drive does work very well for what its intention purpose is. Some uses that we thought: in operational field security, traffic monitoring. Maybe you have a specific host or subnetwork that you want to monitor more because you're expecting something is going on, and you want to be able to throw a box in there and start pulling information off of a tap. Possibly a small portable training environment. If you hardened it and made it a beefier unit to travel more, it would probably work very well for that. Something where maybe you have an operational site that has just very poor bandwidth. You wanted to be able to collect a bunch of logs, but you know that you're not going to be able to send the logs to a central office or location. So you store them locally, and then you can periodically go in and check on them however you would do that. Finally, maybe just computer network defense for small businesses or large businesses that have lots of small remote locations. Total, we got this to about 300 megabits per second, which is not bad for everything. And we'll show you all the capabilities of the box soon. The hardware architecture, we do have a separate firewall, a VPN proxy, as well as an IPS. That was kind of there for legacy reasons. I'm fairly confident it would be easy enough to move into the single virtual box, but it was already there. We just never touched it. We never upgraded it. And what we're doing is we're just pulling everything off of a port mirror, off of a Dell switch. Because they're virtual environments, each of these little red boxes inside the virtual server is a virtual machine right now. And we needed a way to copy all the traffic to all our IDSs, so we used Open vSwitch, which is a module that goes into Linux, and it allows you to treat all your virtual machines as if it were a switch, and it gives you a lot of extra capabilities that the traditional way of networking was not able to do. We have a bunch of extra systems in here, so we do have performance monitoring. We have single sign-on for managing accounts. We also added Puppet and Foreman for doing patch management, configuration management, and a bunch of other things. So there's a lot of extra configurations in here just for managing this single box. The more interesting part of it is what our logging architecture looks like. So what we did was we have a bunch of different log gathering tools, and we're collecting from a whole bunch of different sources. In particular, if you're not familiar, there's a tool called PacketBeat, which is made by Elastic Company. It's free. It's actually pretty neat. It does NetFlow monitoring into Elasticsearch. Suricata is an open source IDS. Bro is monitoring and recording information about all the network packets and contextualizing those. Our syslog, we're collecting from all the Linux systems in there. WinLogBeat we added for if you need Windows. So we have a couple of Windows boxes that we're collecting information from. pfSense and Snort we're also collecting information from. So what's being dropped, what's not, and allows us to contextualize a lot of that. And finally, we have a tool called Moloch, which I'll talk about in a bit. It's a full packet capture device. What it does is it indexes all the information into Elasticsearch and then saves the raw PCAPs so you can pull them out. So you can say, hey, I want to see what HTTP request this is, and I want to see the full packets. It's actually a pretty cool tool for being free. It's made by AOL. I highly recommend people check it out. They still exist. They make a free open source tool that is actually pretty awesome.
I think they're doing a special right now. You can get 100,000 free hours.
So originally, if anyone's ever set up Elasticsearch, the general recommendation was to pump it into all the logs first into Redis, which is a in-memory buffer. I skipped that first because I thought I wasn't that big enough, and I actually did find it was pretty important even for this little single cluster instance. So Redis collects logs, stores them in memory until Logstash can actually handle them. One of the big surprises I had was Logstash was actually the biggest resource hog on this entire system. And Logstash, sort of segueing into it, that is what enriches the logs. So it adds things like GeoIP information of all the IPs it sees. It also takes anything that isn't JSON and turns it into JSON. And you can add all sorts of information. You can send messages to Slack based on certain events, which I'll show, which is pretty cool. And all sorts of other stuff. It's a pretty open-ended, programming type language, and works pretty well. Finally, Elasticsearch is kind of where everything is stored. That's sitting on a single VM. It's, given 32 gigs of resources. It is, pretty big. And then Kibana is the tool that you use to view information out of it. This is a picture of our Slack. So one of the cool things about using Slack for doing like messages and stuff is you can check it on your phone and stuff like that. So this is what it looks like. I get Slack messages when people log in and Slack messages when people connect and all sorts of stuff. So Logstash is what's actually doing that. So in this process, we were able to do about 300 megs, which was what my final goal was. We could probably go a little bit more. We were doing about 4,000 events per second, just from all the different log sources coming in. During that time, the system was using around 90 to 126 watts of power, which is not too much if you're worried about power and efficiency. The three most taxing services were Logstash, Moloch, Capture, and Suricata were the three big ones. This is a picture that we thought was funny because right now this is sitting on my home network, and I kind of creeped my wife out when I was showing her that I was recording everything she was doing. But this is a picture of them making fun of me. So.
Okay, so yes, I don't think Dan made it really clear. That's literally everything he showed you is what's running his home network right now. It's and again, the point of this wasn't. I know it's like, well, it can do 300 megs, but the point of this really was to say how cheap of a box can we get and put like massive amounts of open source capabilities into one box. And that we were actually astonished when we got 300 megs out of it. That was incredible for a box that was $4,000 pieced together on Amazon. So, but so we started looking at it and we said, okay, you know what? How do we scale up? If we're dealing with the customers that we work with deal in the 10s and 20s and 40 gigabits per second, how do we actually bring this kind of capability to them? So the first thing I want to bring up real quick is that the new world, when we talk about virtualization, containerization, SDN, that kind of stuff, in the security context, what we're really talking about as network monitoring folks is that we're not dealing with pipes anymore. We're dealing with individual flows. And once you, once I kind of understood that, things really started to emerge about how powerful, virtualizing could be. So, as an example, a lot of times we think of perimeter defense, we think of a single cable coming in, and we chop that cable, we put a bunch of boxes in between on each side of that, and we start monitoring it. But really that's not the way security works, right? There might be 10,000 clients behind, and each one of those clients making a connection out is a flow, right? So if a client's making a connection out HTTP, there's specific boxes that we want to send it to, but if it's making a connection HTTPS, then there might be other boxes we want to send it to that's not that. So that's some of the stuff we want to think about, that we want to talk about, is that we're not talking about big pipes anymore. We have to look at it as individual flows, and we get a lot of power out of that. So I'm not going to dwell on this too much. Basically, a lot of things are getting consolidated right now. The movement towards virtualizing and data centerizing and all this stuff is to consolidate it. Budgets, at least in our customers, we mostly work in the federal space. Our customers, the budgets are getting compressed really terribly. There's all this brand new open source software in order to do this type of thing, because the application side of the market, the services side, is demanding it. So there's a whole lot of new tools out there like OPNFV, Open vSwitch, DPDK, FIDO, those kind of things that are now emerging, that live up to allow us to, as security professionals, to do some really interesting stuff. So I'm going to skip over some of this stuff pretty quick. Basically, we were going to talk a little bit about multi-tenancy and why we kind of focused on that. The background of this is some of the projects that we worked on were focused around, for our customers, were focused around consolidating network monitoring. So think of it as having one. If you've got a bank with 50 branches, instead of putting an IDS at each one of those branches, we put a big IDS and then route all of the branches through a regional security stack, if you will. So there's a lot of background on how that works. Some of the requirements that we had were in the projects that we work on is that let's say the bank has two different regions. Those regions should be able to go in and not affect each other's policies, which can be a hard thing to do in virtualization. So if you've got multiple firewalls, multiple IDSs, snort boxes, let's say, living on one physical server, if I go in and put a bad rule on my snort box that just bogs it down and eats all the resources, it's going to affect everybody else. So those are some of the challenges and problems that we're trying to solve. There's a higher headquarters example of multi-tenancy. That's where you've got two different sides and then one hierarchy that provides blanket policies. Again, I'm not going to dwell on this too much. Okay. All right, so when we were looking at this, when we wanted to talk about scaling it out and getting into big bandwidths, we wanted to look at bare metal versus containers versus VMs. I know in the security world, containers and Docker is generally a dirty word, but we're looking at how to kind of leverage it to our advantage in the hopes that in the future it's going to get more and more and more secure. And for network security monitoring, generally the tools, you're not going to compromise a snort box by sending traffic through it, right? You would attack it from the side. So we're not overly worried about containers. Anyway, so virtual machines, you've got bare metal, kernel, hypervisor, then another virtual hardware, bare metal, then another kernel, then you've got libraries, then you've got your app. Your app in this case would be something like Suricata, Snort, Elasticsearch, all the stuff that Dan was just saying. The problem with this is that network monitoring, we're doing packet processing. When we do that packet processing, the kernel's your enemy. The kernel is your biggest enemy when doing packet processing. And now we're injecting two kernels. So when we move it over and start looking at containers, it made a lot of sense, right? And when we start comparing the performance of virtual machines and containers win hands down when it comes to packet processing. So that's kind of what we started concentrating on. There's new technologies out. I'm not going to go into depth onto what SRIOV is, but there's technologies out nowadays that are specific to bypassing all of the kernel mechanisms, which allows you to do like 10 gigabits per second on a single box directly to the application and user space. So SRIOV is one of those things. We specifically used SRIOV because it allowed us to pull in many VLANs and then parse those VLANs out to individual applications, and it actually uses the chips in the network card, the firmware, in order to parse the VLANs and send it to applications. So we were able to get really, really high-speed throughputs when using things like SRIOV. That's literally what it's made for. Okay, for this proof of concept, we use this for the high-speed one, the quote high-speed one. We used a similar setup to what Dan had bought for his house. Another Xeon D 1541. Those processors are awesome. And total cost was about $2,300. I'm gonna skip this stuff because the time is going. And long story short, the Intel X710 and XL710 cards are the only cards out on the market right now that allow you to do 10 or 40 gigs while in promiscuous mode. So just keep that in mind. If you want to do virtualize with promiscuous mode with SRIOV, you can't do it without this card. We ended up making a Bro container and a Suricata container. The slides will be available. You can we put that stuff up on GitHub. It's really easy to download. It's a couple commands, and you've got a Suricata box up and running with Hyperscan. Okay, so the results. What do we end up doing? So we took that single box that we just showed you, and we stuck as many containers as we could. We spun up a bunch of Suricata boxes at the same time. We did 1 container, 2 containers, 5 containers, 10 containers, and the Suricata had 13,000 signatures, and we were pushing roughly 4 gigs through it on this little $2,300 box across 10 VLANs. So we were trying to look at the multi-tenancy, and we wanted to see, does spinning up more containers actually affect the packet loss or the amount of throughput? And what we came back with, after certain tuning that you could do, it doesn't really affect it. So if you do this right, you can actually spin up 10 or more containers, and it's not going to affect your throughput at all. So the stuff that Dan was doing, we can actually switch over and then start scaling out horizontally is our goal. Again, SDN is a rotten term, but with SDN you can do some really powerful stuff, and that's really what the future looks like that we want to bring up. So as an example, with your HTTP traffic, let's say the network monitoring that Dan was showing a minute ago, if you bring traffic in, if it's HTTP traffic, then there's certain boxes you want to send it through. But if it's something like trusted services, if there's such a thing as that, then you might only want it to hit certain boxes. If it's DNS, you only want it to go to DNS analyzer. If you know that it's like type 1 encrypted traffic, why are you putting it through your Bro or your IDS or your IPS? It's fully encrypted. You're just wasting your processing power. So you can do things when you're dealing with individual flows. You can send some flows in some directions and other flows in other directions, all with the same individual hardware. And that's really what we're looking at as far as the future goes. So an example of that might be if it's traffic going to an internal server, you still want to send it to Bro, but it'll be a stripped down version of Bro that doesn't use a whole lot of policies. It's only got specific policies that you want. But if the traffic is, say, has a source or a destination of Russia or North Korea, you're going to want to send it to a different Bro. If you look at it as one pipe and send all your traffic to one Bro, you can't get that kind of granularity. But with things like NFV and V switches, you can switch your traffic around internally based on any of the end tuple. So based on the source, the destination, the port, the protocol, all these different metrics can define how your traffic passes all within this virtual context. Again, like things like if you've got a ton of traffic going to Google or Netflix or whatever, and you don't want the Netflix traffic bogging down your IDS, then you can kind of switch it around. Okay, so where we're going with this, we're going to combine these two things together and start scaling out horizontally. We're still kind of learning the engineering challenges of virtualizing a lot of this network monitoring stuff, but we think we've got a lot of those problems licked now between the two proof of concepts that we did. So we're going to take what Dan's done on his home network, and we're work together and basically Dockerize all of it. Now that we see the performance benefits we get from Docker, we've got to look and see what services can be made stateless. Once you can make them stateless, you can basically click a button, spin up 20 of them at once, and they work right on the fly. Or you can start scaling out the hardware, have 20 individual boxes, and spin up a circuit on every one, and tear it down and have your, what's the term when you move VMs around, vMotion type of stuff. And then our real goal is to get this thing going 20 gigs a second. So, that's pretty much all we got. Are we on time? Okay. All right. There's not actually any time for questions, are there? So we'll be around out back if there's any questions or anything, or if you want more